Hey Chemistry, Mrs. KJ here, going over A.06 phases and reactions. And hopefully you already watched this video, which was the Bozeman science. And hopefully that way too, you learned about phase changes being phase changes are for physical. Oh, you know I had to throw that in there. And that you also learned some more about chemical reactions. So just trying to change it up a little bit for you. And so let's just do a quick review. Chemical change. A new substance is formed. That is the key point. You made something new. The bonds between chemicals can be broken, rearranged, and reformed. So you have to come up with something new, a total new substance. Whereas a physical change, the form, not the chemical makeup of a substance is changed. Now, for some reason, people sometimes like to focus on and say cannot be reversed. That's not true because, for example, we can take hydrogen gas and oxygen gas and make water. We can take water and separate it back into hydrogen gas and oxygen gas. So we could say usually cannot be reversed, okay, but not always. And for physical changes, you could say usually can be reversed. For example, if you tear a piece of paper, you can't magically make the paper back into a whole sheet again. You kind of permanently changed it. So it's a usually thing. Just don't get overly caught up on that. Honestly, I don't even like to focus on this at all. I just like to focus on the fact that you have a new substance for a chemical change. That's the main idea. All right, mixtures. If I have a mixture, is that a physical or chemical change? Well, it's two or more substances physically combined, so it's a physical change. I can pick out and eat just the M&Ms. Come on, how many of you like to do that? Okay, you can easily pick them apart. Now, sometimes it's not so easy. For example, if you have sugar dissolved in water, you'd have to get rid of the water and leave the sugar. How do you think you'd do that? So picture in your kitchen, you have a cup of water with sugar dissolved in it. Well, you could just leave it sit there for 2 weeks. And after 2 weeks, all the water would evaporate and you would just have the sugar left over in the glass. And so that's why I included a picture of molecules, because sometimes mixtures aren't as obvious as trail mix. Sometimes it's a little less obvious and we have to think about what the molecules are doing. If they're just sitting next to each other, then that would be a mixture. All right, so let's look at a specific chemical reaction, and giving credit where credit's due. I'm using this reaction, and we're going to take lead to nitrate, which is this almost clear liquid. It's a little bit cloudy, but you would call it clear or whitish. And we're taking potassium iodide. Again, it's liquid. It's pretty clear, maybe a little whitish. And they're aqueous solutions. That's just a fancy way to say that they were dissolved in water. And they are mixed, creating the insoluble precipitate lead iodide. Do you know what insoluble means? Well, in means not, so it's not soluble. In other words, it's not going to dissolve, and it's going to be a precipitate. Do you remember that word? Precipitate is when you have two liquids, you combine them, they have a chemical reaction, and they create what? Usually a chunky, or a little better word here, insoluble instead of chunky, solid. So let's go ahead. And this is a real popular one to show because it's so instant and obvious. Look at that, totally instant, right? So other than a precipitate, what else do you see that shows you that, yeah, that was probably a chemical reaction? Well, you also saw a color change. So that would be another example. This one's a good one to show on video because it makes lead, which is very dangerous, and so you don't actually want to do this one in real life. And you can see here where you're like, well, I can't quite tell it's a precipitate, although when he brought it up, you might have been able to see there were little specks, kind of like little chunks, but he is about to switch it out with one that he let sit overnight. And now you can see how there's liquid, and at the bottom is my chunky solid, my precipitate that didn't dissolve, and it's separated out. You can see as it's swishing, the yellow precipitate's kind of moving around a little bit, but here's a good way to show that, yep, it is exactly as said. We made a yellow precipitate. So again, precipitate, a solid that forms as a result of a chemical reaction between two aqueous solutions. In other words, two liquids are combined, they chemically change, and they leave a chunky solid. So I gave you definitely a more chemical definition, but in chemistry, it's super important to not only know the official definition, but to be able to say it in normal words, because sometimes it's easy to get tripped up and you're like, aqueous, wait, what did that mean again? And it can get frustrating. So recognizing the official definition, very important. Being able to say it in easier words, even more important. All right, so now we're going to jump to the law of conservation of matter, or the law of conservation of mass. Basically says anytime you have a reaction, matter is neither gained nor lost in a chemical reaction. So even though in the video we went from two clear liquids to a clear liquid and a chunky yellow, if we would have measured them and taken the weight or the mass, we would have saw that the weight before was the same as the total weight after. So the mass of the reactants equals the mass of the products. And this is definitely where we're going next. We're going to look at chemical reactions. And we're going to say over here I have CH4. So 1 black carbon atom, 4 blue hydrogen atoms, plus O2, which is 2 oxygen atoms bonded together. When you put this together, you get carbon dioxide, carbon with 2 oxygens, and you get water. So an oxygen with 2 hydrogens. And we're going to talk about how you would actually get 2 copies of this molecule, and we would go back and forth and balance it out. So that's kind of the next thing. But if you look at this, you'll find out that the weight of these is equal to the weight of those. If you didn't catch what I said about the balancing and adding more, don't worry, we're getting to that later. For now, main idea, the mass of what you started with equals the total mass of what you end with. Even if you burn something. So if you take the mass of a piece of paper and then you burn it, if you then took the mass of all the ashes and the smoke and the gases given off, it would be the same. So it's kind of cool. All right, so now we're going to talk about the speed of the molecules. So I'm going to pause. If you feel like, whoa, she's jumping all over the place. Yes and no. These all have to do with physical and chemical reactions. We're just kind of taking it and saying, okay, here's an example of one, here's an example of another. So we are going to look specifically at phase changes. Let's look at this phase diagram. So down on the x-axis going across, I have heat energy. So as I go to the right, I'm adding more and more heat energy, which of course causes the temperature to rise. Now if you're thinking, wait a minute, I thought heat and temperature were the same thing. Technically they're different in science. Heat is the actual speed of the molecules. Temperature is we actually measure how often those molecules bump into something. So the heat, the amount of energy, is going to make our thermometer rise or the temperature rise. They're super close to each other. Most of the time you can think of them as the same thing, but they are technically different, especially in science. And there is one unit where we will really focus on how it's different. But for now, you hear that a lot from me, don't you? But for now, just kind of think of them as being close. So heat, the speed of the molecules, temperature is how we measure it with our thermometer. So let's look. We have our solid. Our solid atoms are nice and arranged. And as we add more and more heat energy, we see that we can melt them, which turns them into liquid. Liquid molecules are a little farther apart. They also move a little faster. And they're a little messier, which makes sense. A solid has a definite shape. The liquids can kind of ooze all over. If we keep adding heat, we have vaporization or boiling. And then we have a gas, where they are going really fast and really far apart. Now, here's the big difference between heat energy and temperature. What do you notice about the temperature during melting? Well, it stays the same. So you'll actually see that in real life. If you put a thermometer inside of a pan, and while you have the ice and it's melting, while it's actually melting, the temperature is stuck at 0 degrees Celsius. Then your temperature will rise, and when you're boiling water, the temperature actually stays the same. Now, but we still got to increase our heat energy. That's because instead of making the temperature go up, the heat energy is being used to spread out those molecules, and only then can the temperature go back up. So that's a good example of how they're different. Even though heat energy affects temperature, the temperature stays the same during a phase change because heat can only do one thing at a time. Heat can either cause the temperature to change or it can cause a phase change. So heat can only do one thing at a time. So heat can do one thing at a time. It can cause the temperature to change, or heat can cause a phase change. So spreading out the molecules or pulling them together based on if you are putting energy in or taking energy out. So if we put energy in, it's spreading out the molecules. If we take energy out, we're cooling off. The gas condenses. So the liquid molecules now are going to be closer together than the gas molecules were. We keep taking heat out, pretty soon we're going to freeze, and then we will have a solid. And so I wanted to give, of course, a visual example of this. Now, if it looks a little bit like it's getting stuck, what's actually happening is it's showing you that at a really, really, really cold temperature, 58 Kelvin, the molecules are really packed in close together, but they're still moving. Molecules are always, always moving. If I speed it up, then you'll see some changes. My molecules are moving faster, and they are spread apart, but they're still all towards the bottom, right? They're still stuck together, they're just kind of flowing. That's a good word for liquids. They are flowing, and then as I get it really hot, now those molecules are moving really fast. They are very spread out. They take up the entire container, and they are gases. So they do not have a definite shape. They fill up the whole container. Liquids also, oh, there we go, it stopped moving on me. Liquids also can ooze or flow, but they only take up a certain amount of volume. They don't spread out and take up the whole box. And then, of course, solids are still moving. There we go. They're still moving. They're packed in nice and tight. And so, again, the molecular difference between solids, liquids, and gases. All right, so let's look at this information. Let's talk about the speed of the molecules in a solid, liquid, and gas. So the speed of solids, slow. The speed of gas molecules, fast. And liquids are just kind of in the middle of everything, so medium. Let's talk about how spread out the molecules are next. So solid molecules are what? They are very close. Gas molecules are far apart, and liquid molecules are medium. Now, I want to jump back to this. Sometimes you'll see that they write down that the solid molecules are vibrating. The big thing is they're always moving. Okay, you have to remember, even if it's barely, even if it's just bumping back and forth into each other a tiny little bit, it's still motion. Definite shape. Think of your computer. Is your computer the same shape every day? Better be. Yes. Liquid. Do liquids have a definite shape? Well, no. If I pour it in my cup versus pouring it on the floor, it's a different shape. Gases? Definitely not. They're having a party. They're going everywhere. What about definite volume? Does your computer take up the same amount of space every day? Yep. Liquids? Yes. If I have 8 ounces of water in a cup and I spill it, well, now there's 8 ounces of water on my floor. So the amount stays the same even though it spreads out. And gases' definite volume? No, it's a party. If you light a candle in the kitchen, pretty soon you can smell it in the living room because those gas molecules are going everywhere. All right, we'll finish up in the next video.